Good evening and welcome to the 10th edition of Fusion EP Talks, student-led webinar in Fusion Science and Engineering Physics brought to you by the alumni community of the European Master in Fusion. Our speaker tonight is Ekaterina Matveeva, I hope I'm pronouncing this sort of okay, who earned her bachelor's degree at the State Polytechnical University of St. Petersburg in Russia and a European Master in Fusion Science and Engineering Physics, both at Ghent University and Université de Lorraine in Nancy. One of her main focus is on high-temperature plasma diagnostics, and I've read that she has quite some experience with Thomson scattering systems. However, her main interest is in studying the physics of abrupt terminations of plasmas in Tokamak, also known as disruptions, which is the topic of tonight, and the one she has chosen for her PhD in Charles University, Prague. So, Ekaterina, the floor is yours. And welcome.
Thank you for the introduction. So I will be talking about disruptions, their causes and consequences, and hopefully, if we will have time, I will show what we are doing here at Compass in relation to disruptions. So the ultimate goal of fusion research is to build a working fusion power plant. And now we gather all the knowledge from Tokamaks all over the world in order to prove feasibility of a tokamak and to show that it's a leading candidate for a practical fusion reactor. And the first step for that would be to build a working ITER and then demonstrate demo. But on the way there, we face lots of challenges, and one of the major issues is an event called disruption, which is sudden loss of magnetic confinement. And disruption doesn't just terminate the discharge. It also leads to significant damage of vessel components, and it prevents sustainable operation of the machine. Therefore, no tokamak-based fusion power plant can be built without solving disruption issue. So I will show what are the phases of disruption, what are their possible causes, consequences, how we can avoid them or mitigate them in the worst case, and then I will proceed to results from Compass Tokamak. This is an example of typical disruption at Compass Tokamak. Disruption is an uncontrolled loss of magnetic confinement, which means discharge termination. It starts usually with magnetic instability, like you can see, for instance, in this graph from internal partial Rogowski coil, which is located here in the midplane, and at the end of the discharge, you see some magnetic oscillations. At the same time, plasma moves towards the wall, as you can see in the heat reconstruction of magnetic flux surfaces in colloidal cross-section. In this case, plasma moves down. At the same time, we lose density. Soft X-ray reconstruction shows that we lose whole thermal energy. Also, we lose suddenly whole plasma current. And at the same time, as this blue curve shows, vessel currents start to increase. And I would like to point out that all this happens at a very short time scale, which is in case of Compass, is about just 1 millisecond. If you put this in a schematic picture, this is an example for ITER expected disruptions. That would be the following. So we have normal operation in case of ITER like 400 seconds, and then a precursor event, which is characterized by edge cooling and therefore steepening of current density profile in order to maintain plasma current. This Unstable current density profile means we have almost no current flowing outside of Q equals 2 rational flux surface. We have steep gradient at the surface Q equals 2, and in the center it's a flattened profile. And resonant flux surfaces will be affected by a steep current gradient, and they will become unstable. This will lead to formation of magnetic island. Then thermal quench starts. During thermal quench, the instabilities that have started during precursor phase, they will rapidly grow, and the island will overlap in radial direction. Perpendicular heat diffusivity will increase. It will be much larger than normally, and we will lose thermal insulation, and therefore we will suddenly lose our thermal energy. At this moment, temperature drops, and temperature drop is followed by resistivity increase. To keep plasma current, we will need to increase the voltage, but present transformers, they cannot produce the loop voltage high enough to maintain the plasma current that we're losing. So we come to current quench, sudden loss of plasma current, which is accompanied by formation of runaway electrons, induction of currents in the vessel, and movement of the plasma towards the wall, and this is disruption. So what are the reasons? Why does it happen? Well, if you read about disruptions or see some talks, you might hear about general rotation of n=1 MHD mode, or auxiliary power was too little, or strong density peaking, large sawtooth crash, some impurity influx, neoclassical Tyrian mode, shape control problem. My favorite one, not clear cause. So I could spend the rest of the presentation just listing the causes. But after all of them lead to violation of operational limits. These are Troyon beta limit, low density limit, plasma current limit, Greenville density limit. And violation of these operational limits leads to disruption. So what are these? Troyon beta limit. In order to maximize fusion power, we want to maximize beta parameter, which is ratio of plasma pressure to magnetic pressure. And it represents effectiveness of plasma confinement. But it cannot be increased infinitely, because magnetic instabilities, such as ballooning mode, for instance, start to develop. And on the figure on the right side, you can see operational space for various tokamaks, where parameter maximum achieved beta is shown in relation to plasma current, minor radius, and Tidal field. So in this case, we see that beta cannot go higher than this line. Plasma current limit. At given toroidal magnetic field, maximum plasma current is limited. This is because kink instability develops. In this case, if plasma column is deformed a little bit, field on the left side becomes stronger, on the outer side becomes weaker, and it continues to deform the column. And it will be stable case if the length of this instability is longer than the length of the Tokamak vessel loop, which is 2 PR. And if we use safety factor parameter. And if we substitute this equation, we will end up with cross-Kolchak-Pramek limit, which states that Q should be larger than 1. And safety factor is related to plasma current. It is proportional to inverse plasma current. And therefore, we can determine that plasma current cannot be larger than this value. But this is ideal case, and in practice, we need to keep Q larger than 2. So plasma current limit will be even stronger. Practically, you can see this in the so-called Hegel diagram that is shown here for jet. So the color represents disruptivity, which is likelihood of disruption to happen. Red color means that quite likely disruption will occur in this operational region, while here in the center, it's quite unlikely that the discharge will disrupt. And you can see that there is no data points on the top. This represents plasma current limit because y-axis is inverse safety factor, x-axis is proportional to electron density radius and inverse to toroidal magnetic field. Another operational limit is Greenville density limit. It means that increase of electron density at constant pressure will lead to radiative collapse. On the operational space, this limit is shown here on the bottom right, and this is empirical boundary, which is not completely well understood now, but what we know is that increase of density leads to excessive edge cooling and radiative collapse. We have various kinds of radiation from plasma, like Bremsstrahlung radiation, which is not that strong and can be easily compensated with heating, electron cyclotron radiation, and line radiation, which is dominant in this case, because here we have parameters that depends on electron temperature, and when temperature drops, line radiation increases significantly, and at the moment when total radiation exceeds heating, plasma disrupts. This is a representative picture from Dexter with symmetric plasma radiation during disruption. Last limit on the left side, low density limit. Here the problem is the formation of runaway electrons. The electrons are accelerated due to toroidal loop voltage, and usually this is compensated by friction that is proportional to density and inverse square velocity. And beyond critical velocity point, electrons are continuously accelerated and run away. I know that previous talk was on runaway electrons, so probably you're very familiar with that. So formation of runaway electrons is dangerous for us because they might damage vessel components with their high energy. This leads us to a sequence of initiating events for disruption. First, there is internal or external cause. For instance, some unidentified flying object in plasma or giant elm. Or it can be external cause, which is human error or control equipment failure, something technical. This is followed by disruption precursor, like shape control loss, impurity influx, position control loss, which leads us to violation of operational limits described above, and then edge cooling by parallel heat conduction, radiation, or convection, and then disruption happens. So why do we care about disruptions, and why do we want to study them? Because they bring significant thermal loads, mechanical loads, and the danger increases with the size of the machine. So for compass, which is relatively small, Tokamak, disruptions are not dangerous, but for jet, they're trying to avoid disruptions as much as possible because they might bring significant damage. And for ITER, it is crucial to minimize the number of disruptions. As you can see from the table, disruption rate for compass is larger than 50%. This is just because we do not care. They are not dangerous for us, and we are not trying to avoid them. At jet, this disruption rate is much smaller, and for ITER, it should be reduced to maybe less than 1%. Thermal loads, here you can see an example of what might happen if you expose a plate to energies of 1.6 megajoules per square meter and make 100 shots. So you can see how everything just melts. And for smaller machines, again, like compass, thermal energy that we store is just several kilojoules. At jet, it's 12 megajoules. At ITER, it is much larger. And I would like to point out that the release of these energies is again at very short time scale. At compass, just 1 millisecond. At jet, 60 milliseconds. And the problem is that if we release thermal energy not uniformly, if it will be focused somewhere, we just do not have the materials that could withstand this kind of thermal loads. Another problem is mechanical load. Even in case of compass, where electromagnetic forces are not that large, still they bring some damage. Like you can see here, this is a casing of one of our Mirnov coils, which is damaged during disruption. For jet, if we count in tons, the forces might be up to 400 tons. And for ITER, again, if we count in tons, then the sideway forces might be like a weight of Eiffel Tower. Runaway electrons also pose significant danger during disruptions. As I said before, usually electrons that are accelerated, they're balanced by friction from collisions, but during disruptions, some of them might be accelerated to relativistic velocities, and they might carry a significant fraction of the disruptive current. And this energy focused in a certain area might melt the material, as you can see in this example from jet. So what can we do about it? First and easiest way is to operate in a safe space. Like if we drive a car, we would follow the road. We will not try to go close to the limits, but this might be boring for someone, and we would like to operate the machine close to operational limits. We would like to maximize density currents. So driving safe is not that interesting for us. What we can do, we can develop reliable mechanical and control systems. And if we see some instabilities that are usually leading to disruptions, we might suppress them in advance so that discharge does not terminate. For instance, if we have locked mode, which is initially rotating MHD perturbation like an island, and it slows down due to friction, at some point its rotation stops, the island growth might overlap with other islands, the transport is increased, uh, we have thermal collapse at the edge, which will lead to disruption, and many tokamaks have these events, and majority of disruptions at jet, they're accompanied by locked mode, uh, and by momentum transfer or shear rotation, we might suppress mode development and avoid disruption. Another thing we can do is to predict when disruption is going to happen. To have enough time in order to start some mitigation techniques. In this case, first of all, we should know to which parameters to look at. Again, such as locked mode, for instance, we can determine a certain threshold of locked mode magnitude, and we know that above this threshold, this is the moment when disruption starts. So we detect this locked mode threshold, and we say that disruption is ahead and we should start mitigation techniques. This requires extensive studies of disruption database at various machines, and machine learning techniques are widely used to do so. And in case if we couldn't predict disruption, or if a prediction was too late, the last option that we have is kind of soft landing, which is fast shutdown before strong major disruption, shutdown that we can somehow control. For instance, we try to avoid large thermal energies deposited on the in vessel components. What we can do is to try to uniformly dissipate the energy, for instance, by massive gas injection or shuttered pellet injection. This is an example from jet with massive gas injection that is injected from the top, and during disruption you can see how thermal energy starts to distribute uniformly. And now, and now I would like to show you what we are doing here at Compass in relation to disruption. Probably many of you have been here during Amtrak, but I will remind you that Compass is a relatively small tokamak based in Prague and Czech Republic. It was developed in 1990s in Cologne, and then in 2007 it was reinstalled here in the Institute of Plasma Physics. It's relatively small. Its major radius is just 56 centimeters, minor radius 23 centimeters, plasma current up to 400 kiloamps. It's very nice small machine. And we have quite a lot of disruptions here. Basically, more than half of our discharges end up with disruption. This is because they're not dangerous for us and we're not trying to avoid them. Disruptions are not a problem for us at all. And that is why Compass is a perfect machine for disruption studies. We have lots of them. The disruption rate varies from campaign to campaign. Like during restart or campaign dedicated to disruption studies, it can be up to 100% of disruptions. And these are the fields we are interested in. first of all, this is asymmetrical disruptions. This means that plasma current is not always toroidally symmetric, and you can imagine it like a tilted loop. And during disruption, part of the current will flow to the wall, and coupled with toroidal magnetic field, it will lead to significant sideway forces. In addition to this asymmetry might rotate, and if the frequency of this rotation coincides with natural frequency of the vessel, it might lead to a resonance and amplification of the forces. It is not a problem for compass, but might be an issue for larger future machines. Another topic we are interested in is measurement of vessel currents, toroidal and colloidal. When plasma moves towards the wall during disruption, there are currents induced in the vessel, so-called eddy currents. And when plasma is in contact with the wall, there are also so-called halo currents that are flowing along open magnetic field lines, then to the vessel, then back to open field lines. And there are various theories that predict what are the maximum values of these currents, and not all of them are consistent with experimental results so far. So what we are trying to understand here at Compass is what is the maximum limit of these halo currents, how they are distributed in toroidal and colloidal direction. And the last thing is project we have started recently with ITER, when we are studying current flows towards the wall, towards diverter during disruption. This is in order to validate asymmetric toroidal eddy current model. This model might explain plasma current asymmetries that we observe, and it states that there are some vessel currents, and when plasma is in contact with diverter tiles, there is a possibility that we have a parallel contour of currents, and these vessel currents, they flow through the diverter tiles, they jump through the gap through the plasma to another diverter tile, and therefore we have another circuit of current that is flowing here. And usually we do not measure any currents at diverter tiles here, and we do not take this effect into account when we talk about sideway forces from these vessel currents. So this is another topic of interest for us. And I see that half an hour passed, so I will jump to conclusions.
You can take your time, don't worry.
It's fine.
It's not necessarily strict, so if there's something else you want to go through, just...
I showed what we are interested in at Compass, and the rest I was counting on like extra slides, which those who are interested might take a look later maybe. So I would like to point out that first of all, we cannot achieve reliable operation of future large tokamaks without clear understanding of what are expected thermal loads and especially electromagnetic loads, which means understanding of vessel currents. We need a clear correlation between theoretical predictions of electromagnetic loads and current experimental results. And as for Compass, we have a large disruption database. They are not detrimental for us. We have advanced magnetic diagnostics that allow us to study plasma current asymmetries and vessel currents with their colloidal distribution, and we can measure them in several toroidal locations. So we have really nice set of diagnostics and lots of possibilities to study disruptions. And you're always welcome at Compass to take a look and see what we're doing here. Thank you very much.
Thank you. That was a great talk. I really enjoyed it. So the floor is open for questions. Go ahead and raise your hand in the participant box or type in the chat box if you prefer. Okay, while you think your questions, maybe I'll go ahead and ask a couple.
Okay.
Would you be so kind to explain what you meant by unidentified flying objects in a tokamak?
This is not what usually people think of. This might be a piece of dust or something was a bit broken during previous discharges, and a piece of vessel components just drop and fly inside the vessel. This produces very beautiful videos with lots of sparkles after all.
So that would cause like a radiative collapse.
Yes, exactly. This will increase the density and increase of impurity radiation.
Okay. Would you also mind clarifying a little bit more the concepts of like eddy and halo current? I'm not so familiar with it.
I have to say that especially definitions are not widely accepted in scientific community, and there are some people who claim that there are no halo currents and there's other so-called halo currents. I would say there is no clear answer of what are the currents flowing in the vessel and where does it come from. But how I understand it so far is that first, when plasma moves, there are some currents induced in the vessel that try to prevent movement of the plasma column to the wall, and these are eddy currents. They are usually colloidally symmetric, and this is this red line. And with halo current, there is a concept that states that particles from the plasma core diffuse to the open field line, and they are dragged along this field line to the vessel, and then they come back to the open field line. And these halo currents, they might be limited. Some people say that they are limited just by the number of particles that are contained in the plasma. And this is what we would like to study, what is the maximum of possible halo currents. And these are not colloidally symmetric. For instance, this is a picture from Compass. Here we measure colloidal currents in 24 colloidal locations. So x-axis is time, and here are various magnetic coils that allow us measurements of colloidal currents. For instance, this line represents measurements from this coil. This line comes from coil number 12 from here, and so on. So this upper part of the plot represents upper part of the vessel, and we could see during upward disruption that there are some currents that are not colloidally symmetric, and we believe that these are Taylor currents that appear here, um, and they might be up to 50 kiloamps during current quench, which is almost 20% of predisruptive plasma current. This is quite large value.
So essentially, the point is that those are very large currents that could then induce large mechanical stresses on the vessel that come from the disruption.
Yes, exactly. And if we don't know which currents to expect, we don't know which forces to expect.
So one more thing I'd like to ask is you've shown that I think at some point that jet became more disruptive after installing the ether-like wall. What is that attributed to?
Yeah, true. Here, because basically, when they installed a new wall, they had to learn again how to operate the Tokamak. Because the operational space I was showing before, it was not well defined at that time with new conditions, especially with Greenville density limit, for instance. It depends also on how pure plasma is. So change of the wall affects this limit significantly. So I guess that quite a lot of disruptions, they were in the first phase of operation.
So did this reduce in more recent experiments, or is there no data yet?
I've seen an article with disruption statistics in time. I don't remember clearly now, but I think now it's smaller than it used to be in the beginning, if I'm not mistaken. I'm not sure.
Okay. Last chance for questions, comments, objections. If not, well, let's thank the speaker again. And thank you all for joining us tonight.
Thank you very much for the invitation.
And next week, no, not next week, the next talk in 2 weeks is going to be about tritium traps for the International Fusion Material Test Facility. So if you're interested, please join us. And until next time, have a nice evening.